Hello, everyone. Our project is called the Smart Eco Kettle, and it's an energy efficient and intuitive redesign of the electric tea kettle. This is an outline of all the things that we're going to cover in the presentation today. And now we're going to introduce ourselves. My name is Marvel Pilati. I'm an electrical engineering major. I'm the team leader for this project, and I'm also the wireless communication and software lead.
Hi, everybody. My name is Charles Barnes. I'm the computer engineering major, and I was the hardware design lead.
Hi guys, I'm Alec Perron. I'm the electrical engineering major, and I'm also the circuit design lead.
Okay, so now we're going to cover some of the motivation behind this project. One of the reasons we decided to do this project was because we saw the growing international kettle ownership rates, especially in places like Asia, Africa, Europe, and even in the United States, where electric tea kettles have been largely unpopular. In Libya, for example, about 42% of all households owned a kettle in 2013, and that's up 8% from 2008. In the UK, about 97% of households own a kettle. 40% say they use it multiple times daily, and 40% of all cooking electricity consumption by 2030 will be from electric kettles. So they've been around for a long time, but electric tea kettles haven't seen much innovation. And there's a good reason for that, mainly because electric tea kettles are already one of the most efficient ways you can use to heat up water, even more efficient than microwaves or any kind of stovetop cooking methods. But still, that doesn't mean there isn't room for improvement. And there are a couple of problems that we believe we can address. So one major problem is the demand spikes. So the electric tea kettle is one of the appliances that has the highest power requirements when switched on. And this is evidenced by high spikes caused by kettle usage in otherwise the low to medium demand profile of a typical household. And due to the spiky nature of the demand, the kettle can significantly influence electricity generation and the power distribution network. And in the UK, where a lot of people own kettles, this effect has its own name. It's called a TV pickup effect, and it's apparent during breaks in popular TV programs where a lot of people go and turn on their kettles all at once, and this causes a lot of instability in the electric grid. Another problem is the overfilling and reboiling. In the UK, about 75% of households overfill, wasting about 68 million pounds annually. People don't measure out how much water they need, and the excess water being heated gets wasted. And same thing for reboiling. People turn on their kettles and walk away, forget about it, and when they come back, all the energy that went into heating the first kettle is now wasted. So are there solutions in the market right now that address these problems? Well, sort of. There are solutions out there, and some of them you can see on your right. But the problem is that they don't address all the problems, or they have too many trade-offs. Either it costs too much, or it's too impractical for consumers, or they're just ideas and they haven't they aren't on the market currently, and they're just ideas that like ours that need to be built and proven. So what is our solution? So we hope to address these problems that we mentioned by moving most of the functionality to a mobile platform. By separating the kettle from the kitchen and putting most of the control on your phone, which most people have on them all the time, you reduce the possibility of human error and automate the entire tea making process. Now that the user can specify how much water they need heated and to what temperature, the microcontroller will be able to do that job automatically for them. Furthermore, they can schedule times for the heating process and begin automatically, which can shift the load to earlier times and prevent the spike in demand that causes instability in the system. So to summarize, we believe there's a demand to develop an electric kettle that can alleviate pressure on the electric grid and also reduces overfilling and reboiling by the consumer. Who benefits and who is affected? Well, the consumer, because you've automated a large part of the process for them and made their lives easier. The electricity companies, because you alleviated a lot of the pressure on the grid, and the environment, because you're saving power consumption, reducing waste.
So here we have our system architecture diagram. This is inspired by the functional decomposition level 1. So as you can see, there are many modules that go into our project. First, you have the power supply that supplies 5 volts and 2 amps. That goes to our Arduino or microprocessor. Then you have a serial connection going to the Bluetooth module. This sends a single bit, 1 or 0, to our valve to either turn it on or off. Then that water flows from the reservoir into our kettle. So also from the Arduino, you have 3.3 volts GPIO power that goes to our IR temperature sensor. And the temperature sensor outputs temperature inside of the kettle and feeds that back to our microprocessor. Once the microprocessor reads that information, it determines whether to keep heating or maintain the temperature or stop heating the system. The microprocessor sends a power output to our induction coil, and depending on what happened in the previous step, whether to keep heating, maintain temperature, or stop heating, the induction coil is going to heat the water or stop functioning altogether. So here we decided to include our data flow diagram. So you end up with, I believe, 5 modules here: the UI, microcontroller, database, cloud server, and application or display. So the UI sends unfiltered signals to the microcontroller. That unfiltered signal goes through data correction, becomes a filtered signal that's sent to the database. The database sends simplified data to the cloud server for data analysis, and the analyzed data is then sent to the phone, application, or display. So for our related theory, we use equations from the Biot-Savart law and also coil inductance equation for our induction heating application. So we use induction heating because it's a non-contact heating process that uses high-frequency electricity to drive AC current through a load. The current produces a changing magnetic field, which induces current flow in the kettle. And the high frequency is used to, it gives rise to the skin effect, which increases resistivity. And the Biot-Savart law can be used to find the magnetic field due to the current. And also our coil inductance is explained by this equation that relates inductance to the coil outside diameter, number of turns of the coil, and the length of the coil. So here we have our design and implementation for the hardware. So due to COVID-19, we had to switch a lot of our simulations to PSpice. So primarily we focused on 2 instances for our induction heating element. One is where the circuit is filtered and has power factor correction through parallel tuning. This first schematic shows without tuning, and this is a bad scenario because, as you can see from the graph on the right, we have a spike that goes to 200 kilowatts, and then it levels off to around 12 kilowatts. We don't want this spike because it's an excess draw of power. Our second schematic shows tuning. The circuit is LC tuned, and it's also corrected with the power factor correction of the parallel circuit. This produces a more desirable result. As you can see, it only goes up to 20 kilowatts and then it levels off to 12 kilowatts, which is a more desirable output power. On the second circuit, we decided to do more analysis to figure out where the optimal frequency would be to deliver the maximum current to our load. So we figured that to be around 30 kilohertz, and that that provides a current of around 2 amps into our load. So since our kettle focuses on overfilling and user preference, we need to consider a water reservoir and valve setup for our kettle. So last semester we tested this setup by mounting a pipe to a water bottle and setting that up with the valve. And the valve is connected to a solid state relay that provides 110 volts to the system, but only isolates us to 5 volts. So this valve is normally closed when there's no voltage applied to its terminals, but when 110 volts is AC is applied to the valve, it'll open, and that'll allow the water to flow from the reservoir into the kettle. As you can see on the right, we also have 2 CAD drawings that are our proposed reservoir designs. Unfortunately, we couldn't bring these designs into fruition because they were sent to the 3D printing process, but we couldn't get them due to the current situation. So here are our developmental iterations for optimal hardware. So before we started prototyping, several iterations had been made to take health and safety into consideration. We had to consider water isolation because electrical shock is a possible hazard. We also had to consider electrical isolation. Since the valve operates at 110 volts AC, we don't want our user to be exposed to such a high voltage. So the relay was used to isolate the user end to 5 volts, while also providing the terminals of the valve to 110 volts. And part specifications also had to meet our minimal operating conditions, as well as ensure a sustainable and safe system.
Okay, so now we're going to talk a little bit about the design and implementation of the software. So this is a block diagram that shows the flow of information within the entire electrical system. So on the far left, you could see the mobile app, which is what the user will input instructions into. And the information from the mobile app will be relayed to the Arduino, which houses a microcontroller using the HM10 Bluetooth Low Energy module. And this module will relay information back and forth between the app and the Arduino. The Arduino is the brain of the entire operation, so it'll take inputs from the user and also take inputs from the temperature sensor and the water flow meter. And using those inputs, we'll be able to determine the inputs for the solenoid valve and the induction heating circuit. The valve will determine how much water will be released into the kettle, and the induction heating circuit will determine the temperature of the water inside the kettle. So we talked a little bit about the induction heating circuit, and now we're going to talk about how the Arduino controls that circuit specifically. Obviously, we can't control the heating circuit directly using the Arduino because this circuit is a high voltage circuit, and using the Arduino to control this would be impractical and pretty dangerous. So instead, we'll be controlling the induction circuit, heating circuit, indirectly by using the Arduino to produce a pulse width modulated signal, which will control the switches of the half bridge inverter we see here. So on the top left, you have a picture of what is a typical half bridge inverter. On the left, you can see that there's a DC voltage input, and this will be transformed into an AC voltage signal at the output, which in our case will be the induction coil. So in traditional systems, this is done using a comparator and 2 voltage signals, one voltage signal being the reference voltage and the other being the carrier. The difference between these 2 signals will produce a pulse signal you see here, one of which is directly sent into the gate of one MOSFET, and the other which is inverted and sent to the gate of the other MOSFET. This, along with the LC filter, will produce the AC voltage signal you see over here. In our system, we can replicate this using the pulse width modulation feature of the Arduino, specifically the analog write function. And by adjusting this function, we can instantaneously control the inputs of our gate and therefore control the voltage at the load. So this is a flowchart of our code, which we'll run through very quickly. At the very top left, you can see how the process gets initiated, either by the user scheduling a time to initiate the heating process, or by manually pressing the on button. After that, the app will check if a device is connected. If not, it will ask the user to scan and connect to the device. Up next, it will check whether the kettle is filled or not. If it's not, it will fill the water from the reservoir, and then it will start the heating process. The heating process consists of two steps. First, the current water temperature will be compared with the desired water temperature until that desired temperature is reached, while at the same time, current water temperature readings will be sent to the mobile app so that the user can see them on the phone. This happens until the desired temperature is reached, at which point a push notification is sent to the user, alerting them that the entire heating process is finished. If the keep warm function is enabled, the system will maintain the desired temperature within the kettle until the user manually turns the kettle off. Otherwise, it will stop automatically. So here we have two pictures. On the left, you can see the mobile app, which is what the user will have access to. On the top, you can see the scan connect buttons, which the user can use to connect to the kettle. Right below that is the status label, which will give you the current status of the connection between the two devices, whether it's connected, disconnected, connecting. Right below that is the on-off button, which the user can use to initiate the heating process. Right below that will be the current temperature readings sent from the Arduino. Right below that is the temperature slider. So using this slider, the user can adjust what temperature they want their water to be heated to. Right below that is the keep warm switch, and then right below that is the schedule switch. So when this switch is enabled, a time picker will appear at the bottom, which the user can select and then set the time they want for the heating process to start automatically. On the right, you could see the physical layout of our entire system. This is a top-down view. You can see the Arduino temperature sensor, the BLE module, and the indicator, the LED indicator over here. This is just to show how all the pins were wired and how our system was configured, how it looked from a breadboard. So now we're going to talk a little bit about the developmental iterations that we use to achieve an optimal software design. So on the right, you can see the picture, and this is how far we came from the fall semester. On the left is what the app looked like at the end of the fall semester, and on the right, this is what you saw in the picture before. This is the final version. While the mobile app was only a small part of the entire software, this is a good visual indicator of how far we came on this project. So at the end of fall, we only had one-way communication between the two devices. We could only start and stop the process. The user had no way of getting updates on the temperature on the phone because, again, we only had one-way communication. And the user also had to manually enter the temperature that they wanted. And this was unintuitive because they could make a mistake and then the whole process could fail. And there was a lot of possibilities for error. And there was also no option to schedule automatic starts for the heating process. This was all implemented during the spring semester. There are also different considerations. Alec talked about this earlier: isolation between the control system and the high power circuit. This was done using relays to separate the sensitive Arduino from the high power circuit. Also, Bluetooth low energy connectivity was used over Wi-Fi and Bluetooth Classic. The difference between them being that instead of having a constant connection, we have a short-term connection that sends small data packets with low data rates. But this was acceptable for our design because it was far more efficient, about 30% more efficient in similar tasks. That means we saved on power consumption, which saved on money, which is beneficial and acceptable for our project. And now we have a small video showing our project and some of the functionality. So here the devices aren't connected yet. See that here, it's disconnected. I'll scan for devices, the start device, and I will connect to it. And the status label will now say now it's connected. I'll turn it on, and you can see that the LED turns on, indicating that there's a secure connection between the two devices. And right below that, you can see the water temperature, which was recorded using this infrared thermometer over here. And that went up when I put my finger over it. And this is a temperature slider that the user can use to set their desired temperature. If it's at 81 and the temperature reaches that desired temperature, you'll immediately get a notification on the phone saying that your tea is ready and that the heating process is completed. So that's how the system would operate. We could complete it. There's a keep warm switch and the schedule switch over there. And if you hit that set time button, you can set the time. And I set it at 11:10. I don't know if you saw that. I set it at 11:10, which was the time, which was the current time. And because of that, it automatically turned on, initiating the heating process.
All right, now we're going to finally get into the testing a bit throughout the construction of this project. During the fall, you notice a lot of our tests were done in November. These include various unit tests for the original version of our circuit, the one we saw earlier in the video, with the breadboard and the water and the kettle. There was Bluetooth functional test, valve, mobile apps, and the Arduino itself, as well as the temperature sensor. And then it culminated in a synthesis of the specific modules. This semester, pretty much we had 3 main tests we had to switch over, boards-wise, as well as test our final induction circuit, which is still, what do you call it? Which is still doing well. We had various iterations due to in some instances, issues with connections, issues with code, issues with hardware, and over the course of the semester, this one in particular, we experienced a lot of difficulties, specifically in, as we noted before, with the CAD drawings and the fabrication of our final housing, as well as circuit design, just because ZVS is hard to manipulate. But beyond that, we still did a wide variety of tests over the course of the semester. And then we had a couple, this semester in particular, we were really really digging into the physical induction circuit, which realistically, due to the Corona situation, we've switched to simulating that purely with PSPICE simulations and analyzing the graphical results. In addition, we have the gate driver circuit, Arduino control system, as well as synthesizing all of that into the bottom 2, as you see on the screen. The water reservoir, basically the final end of the project that the user would be interacting with directly. Those were difficult to manufacture afterwards, so instead we substituted the theoretical work behind it. So for instance, the software as well as the design drawing, so what it would have looked like, which got all the way up to the 3D printing office in the mechanical engineering department, but unfortunately they closed like the rest of New York for now. So this project actually brought us, at least brought a lot of new skills to our team. For instance, we used the MIT App Inventor for the first part and the Arduino IDE, which was new. I personally had experience with AutoCAD for the first time, which I had never. I've been working in, I've been interning in electrical companies, but I'd never been able to use AutoCAD before. And so this, even doing simplistic designs on our proposed housing unit was very interesting. I got to involve a couple of my roommates in helping me learn the process, and as well as taking an actual in-depth look at what the 3D printing process actually looks like. It was very interesting. But anyway, for the future work, if we had more time and things that would be furthering this project down to get it to that final stage where it can directly interact with the customer or the user, we'd have to refine the circuit elements, finally get that construction housing unit, at least, sorry, excuse me, get the housing unit constructed, do a couple final integration tests, and then also possible, like a PCB. Those are just a couple of possibilities of future work. In total, over the course of the 2 semesters, we spent about 185.48. This is all from the first prototype to the second. Actually, we came significantly under what we could have spent for this. We tried to get our housing unit built earlier, excuse me, and without even with the school, and we were quoted a sum of $900. So we actually got a pretty good bargain out of what we spent for now, being that 3D printing at the school is free. So we have a total $185.48, and the remaining school budget out of the 250 is 64.52. So that's the total, each of those individual parts. So finally, we had to do a lot of consideration with our design. Primarily, what we're building is a device that heats water, so it needs to be potable. So in our first standard, our first code rather, is the OEHHA proposition, which is California's Prop 65, which prevents or at least prohibits, serving toxic drinking water to customers. So what we needed to do was consider that within our design element, isolating and taking into consideration the specific elements we introduced to the water. So we couldn't really use a treated pipe to interact directly with our water, so we needed to make sure everything was sanitary and clean. And then the IEEE Bluetooth standard, which caused us to, we had an HM10 Bluetooth module, which falls within the requirements for security as well as connections. And then the RS-232, which is just the governance on the serial communication, which is also seen in our Arduino circuit. So everything is compliant. And then the NIST, NIST electronic compliant, which basically our circuit won't explode. So we did pretty well there. And that pretty much stands. And now for our ethics, the ethics section of this project, really what we were looking at is how is this going to affect the world at large, society. Well, really what we wanted to do, early we covered it, how this would drastically reduce the TVT problem, drastically reducing the electrical load on the entirety of grids everywhere. So that could be, societal impact, environmental impact. Predominantly, what we hope for this project is to get it in the hands of everyone who drinks coffee and tea, ideally, just really butt into the market share. So all personal user data associated with that, times, wake, productivity levels, you name it, could be part of the scope of this project. And we need to make sure that our software remains compliant and secure. And realistically, we built this project as a means to help and not to harm others, which is within the realm of the code of ethics for IEEE at large. So really, that's most of our ethical considerations, which we fall pretty well, and this thing will help once it's finished. And these are finally our references. If you have any questions, please feel free to ask. Thank you very much.
Thank you.
Thank you, guys.